Hello everyone, welcome back to this lecture series on the thermodynamics. This is Dr. Rahul Srivastav, Assistant Professor, Department of Physics, Bhopal School of Social Sciences, Bhopal. As we have started this lecture series on the basics of the thermodynamics, and we have a detailed description of the basic thermodynamic systems followed by the various laws. These are the four basic law we have discussed, that is zeroth, first, second and third law in the previous lectures. In the today's lecture, since this is the second lecture, so we will go in the applications of the first law of thermodynamics, and these are the some having special application part or some practical part that we will discuss in this lecture series. So today's plan of talk is first we will discuss the first law of thermodynamics, a brief description since we have already covered in detail in the previous lecture, so you can go through it in the previous lecture. We will have some brief description of first law of thermodynamics followed by the applications of this. From there this portion we will have some detailed description on it or a zoom it on it. So these applications are having some special processes that we will use it as in our application parts, that is the isothermal process, adiabatic process, followed by the isobaric and isocoheric process. These four processes defines the application part of the first law of thermodynamics. So let me start with the basics of the first law of thermodynamics, as we have already covered it. So we will have some short description on it. So first law of thermodynamics is basically a law of conservation of energy. It states that the energy is getting changed from one form to another form. So when a mechanical work, that is the one form of energy, is completely converted into heat energy towards the another form of energy, that is what the energy conservation law, or vice versa, means the heat is converting back into the mechanical work, then in each state of the ratio, in each state the ratio of work and heat always remains constant. So mathematically we can say that the W upon Q is equals to J, or a constant value, where W is the work done, whatever the mechanical work we are having, also followed by the Q is the heat, we are giving the input heat so that we can have this mechanical work, and after that the J is a mechanical constant value or the mechanical equivalent of heat. These values that has to be differentiated, because we are going to discuss about the change in heat or change in work. Since we cannot have all the time constant values, so that has to be changed with respect to time. So if dq is an absorbing heat to a system, means the heat is getting changed after the absorption and before the providing conditions, and because of this the change in internal energy of a system we are taking taking it as du, followed by the dW is the total work done we will have from this absorbing of heat process. So dW is the total work done of the system. Then the importing heat will equals to the summation of these increase or decrease in internal energy plus the total work done. Mathematically we can say that dq is equals to du plus dW, where we already know that dq is the importing heat, whatever the heat we are providing to a system, and this heat is getting changed with respect to time, so we are saying it as dq. Followed by the du is the change in internal energy because of this heat absorption process of the system, and after that the dW is the total work done or the mechanical work we are having. So the application part begins from this this particular discussion here also, that the various processes we are having. Since the thermodynamic process have some variables, so these variables are temperature, heat, followed by some internal energy and some other parts. So we will constant one part or the one variable, and we will have application point of view from this first law of thermodynamics. For example, the thermodynamic variables we are having. So let me introduce these. The first one is the temperatures. We all know that the temperature is the degree of hotness or coldness of a body, that how much temperature of a body is having. Followed by the heat, the absorbing temperature is basically the transfer of energy from one body to another body in the form of temperature is known as the heat, or the flow of temperature from one object to another object. Followed by the pressure, the force per unit area on a specific unit area, whatever the amount of force we are putting on it is known as the pressure, the overall pressure of a body. And the volume, measurement of a occupied space in 3 dimension is the volume. So we are taking these 4 thermodynamic variables, and we will constant one variable and the remaining will change. So while constanting this particular variable will give its name. For example, the if we are constanting temperature or the other 3, heat, pressure and volume is getting changed. So this process is known as the isothermal process. Similarly, for the if heat is constant, this is known as the adiabatic process, and if pressure is constant, then this is known as the isobaric process, and the last one is the if volume is constant, this is known as the isobaric process. So let me start with the isothermal process. As we have discussed that the particular temperature of a system will remain constant. So the statement of this isothermal process is, if the thermodynamic state of a system is changed in such a way that the temperature of a system remains constant, means the temperature is not getting changed. We have provided a temperature to a body, this will remain constant in whole process. It will not get changed as the process go further. So in image we can say that the volume is getting changed since the volume is the volume of this piston, since the piston is moving up and down, so volume is getting changed. Since volume is getting changed, so the pressure, amount of pressure putting on this piston, that has also been changed, and also the change in internal energy we will have. But the temperature on the right side we can say see in the image, the temperature is not getting changed. We have provided the temperature once, and heat is getting changed, heat is transferring from one place to another place, but temperature is constant in whole process. So since the internal energy of the system basically depends on its temperature, so since there is not any change in temperature, so there will not be change in internal energy also. So we can say that du is equals to 0. So mathematically, from the first law of thermodynamics, we have dq is equals to du plus dw. Since du is equals to 0, we are putting on in this equation. So after all, final equation we are having dq is equals to dw, and it is saying that in isothermal process the total heat absorbed by a system will be equals to the overall work done. It means that there will not be loss that is getting by the internal energy. So this is a kind of ideal situation where we are providing heat to a system and it is completely converted into the work. So if we are providing heat to this piston, so whatever the heat we are giving to it, it is completely converting into the mechanical work. So there will not be any absorption of heat via internal energy. So internal energy will remain constant, or change in internal energy will be 0. So this is what the isothermal process is. After that, we are having the second process. This is known as the adiabatic process, and we have already discussed that the temperature will change but heat will remain constant. So we can as we can see in the image also, in the right side, temperature is changing as far as the process is going further, and this temperature provided to this piston is also providing the change in volume, and the amount of pressure is also getting changed, but heat is constant in this particular process. So if the thermodynamic state of a system is changed in such a way that the heat of the system remains constant, so this process is known as the adiabatic process. So if heat is not getting changed, heat is constant, so Q is equals to constant, so that dq, or the change in heat, will equals to 0. So what we are trying to say, that we have given a temperature to a system and this temperature has been converted into the heat once. This heat will not change in any state of the thermodynamic process. So this is known as the adiabatic process. So dq is equals to 0. So according to the first law of thermodynamic equation, dq is equals to du plus dw, and this will equals to 0. We are putting in 0 in place of dq. 0 is equals to du plus dw, or we can say that du is equals to minus dw, or dw is equals to minus du. So what we are having here, so if the heat is not getting changed, it means there is not any outside force or outside energy towards the piston, so that this work done, whatever we are having, because of the the internal energy a system is having. Since temperature we are providing, so definitely there is a change in internal energy also there, and this change in internal energy actually providing the work done. So du is equals to minus dw, means if internal energy is increasing, then the work done is getting less. So we are having a less work done or a negative work done here there. And if we are having some work done or the positive work done, some extra work we are having from this piston, then that work means the piston is going up and down, up and down. So if we are having some extra cycle of piston going up and down, so this is because of the internal energy. So in adiabatic process, the work done we are having from the system, the internal energy will have some decreasing part or vice versa, as we have discussed. So this is what the adiabatic process is. After that, we are having some isobaric process. As we all know that in this process the pressure of the system will remain constant. So in the image we can see that the temperature is getting changed. As the temperature is getting changed, the heat inside this piston is also getting changed, and the volume of the system, as we are seeing this is going, piston is going up and down. So the volume of the system is also changed, but the pressure, the amount of pressure that piston is coming back to its own position is constant. It is not getting changed. So this process is known as the isobaric process. If the thermodynamics state of a system it changes in such a way that the pressure of the system is remain constant, then this process is known as the isobaric process. So if dV, we are taking V as a volume, as we have discussed, volume is the three-dimensional calculation of a piston or a area. So if V is a volume and dV is a change in volume with respect to time, and this change in volume because of the constant pressure, we are using constant pressure because this is isobaric process. So if pressure is constant for it, so the change in volume is dV, then overall work done dW is equals to P dot dV. This is the work done equation we are having from the mechanical system, that whatever the work done we are having, this is because of the amount of pressure we are putting or a system is putting on a piston, and volume is getting changed with respect to this pressure, and heat also will be there. So the work done means the piston is, how the piston is going up and down, up and down. In the next lecture we will focus on the heat engine, and we will discuss more and more that the movement of piston, that how we can have the work done. So here the work done is meaning that piston is going up and down, up and down. So if piston is going up and coming back to its own position, so we will have 360 cycle rotation of a wheel. So by this process we are having the motion of our vehicles, cars and bikes. So if piston is going up and coming back towards its own position, means we will have a complete 360 rotation of a wheel for a one time. So this is a continuous process, so that our wheel is continuously rotating, and this is how our system actually works. So we will have more and more detailed description in the next lecture. Today this is the dW is equals to P dot dV. So this work done is actually a mechanical rotation, a 360 rotation, and we are having this rotation because of this pressure we are putting on a piston, along with the change in volume dV. That change in volume is the piston going and up and down. So this change in volume is piston's volume is getting changed. So P dot dV. So we are putting this value on the first equation, as we have discussed from the started, dq is equals to du plus dw, or we can say that dq is equals to du plus P dot dV, where P is the pressure and V is the volume. So we can say that in isobaric process, absorbed heat of the system is equals to the change in internal energy with respect to the constant pressure and change in volume. So this is what the isobaric or a constant process. Last, the isocoheric process. In this process, as we are seeing in the image, the temperature is getting changed, heat is getting changed, volume is constant, and the pressure is also changing. But the volume is constant, it means the piston is not moving. Once the piston is not moving, it means the change in volume is zero. Once the volume has been fixed, the volume is having certain value but a constant value. So if we will discuss or we are going to differentiate it, so then dV is equals to 0, or the change in volume is equals to 0. So what is meaning that there is not any work done. So, if the thermodynamic state of a system is changes in such a way that the volume of a system is remains constant, it means that the dV is equals to 0. Once dV is equals to 0, so according to the first law of thermodynamic equation, dq is equals to du plus dw, and in place of dw we can put p dot dv, and in place of dv we can put 0. So, we will have dq is equals to du. So, we are saying that if piston is not moving or the volume of a piston is constant, means the piston is not going up and down. So, that if the piston is not going up and down, so there will not be any mechanical movement there or the mechanical rotation there. So, since we are not having any mechanical rotation, it means that there is not any work done here. So, dq is equals to du, and it is saying that in isobaric process the work done is by the system is 0 in this particular process. Since piston is going up and down, so we will have some work done. If piston is not going up and down, so we will not have any work done. So, du is if dw is equals to 0, means there is not any change in work. So, overall work done in this system will be remain 0. So, whatever heat we are providing, that is completely absorbing by the internal energy. So, that dq is equals to du, that is change in heat, is equals to change in internal energy, and the total work done is 0 in isobaric process. So, we have discussed the all basic applications of first law of thermodynamics in this particular lecture. In the following lectures, we will discuss more and more about the heat engines and some other engine, the practical engines also there. So, so for this particular lecture, this is Dr. Rahul Srivastava signing off. Have a nice day.